So good morning, everybody, and welcome to another research seminar. Today we have here maybe yes, no better no yes. We have with us Amin, who is going to give a talk about titled 22 Nobel Prize and the Challenges of Bell's Inequality, Closing the Freedom of Choice Loophole. So Ricardo will make the official introduction.
Okay, thank you, Miguel. Thank you, Amin, for coming. So you already mentioned the title of the talk. So Amin is coming from the University of Vienna, and he's working there with a group of Anton Zeilinger, who is the Nobel Prize awardee in 2022. And he specializes in quantum optics and quantum information, and he's working in this group. And he will be talking today about some of the topics that that are the motivation of this Nobel Prize in 2022. In particular, Bell tests and tests of the violation of the Bell's inequality. So these are experiments that started a long time ago, and in particular, I think he will be talking about an experiment that some of these experiments, probably some of you know, were carried out in our observatories, in particular a paper in 2018 that proved this inequality in cosmic scales using light from quasars. So I think he will be mentioning and emphasizing this result during his talk. So Amin was a PhD student in Iran in the Institute for Advanced Studies and Basic Science, and then during that time he started collaborating with the group of Professor Zeilinger in the University of Vienna. After his PhD, he moved to Italy for a postdoc position. And after that, he started working as a postdoc in the University of Vienna in 2021. And he's been there ever since, when he's been carrying out research on these topics. So, I mean, the floor is yours, and thank you for coming. And it's a pleasure having you here.
Thank you. Good morning, everyone. I want to express my thanks for the warm introduction, and also thanks for the Institute of Astronomical Physics in Canary Island to give me this opportunity to talk about our groups, what we did in previous and what we are looking for in the future. As it is clear from my the topic, I will talk about the 2022 Nobel Prize and the people what they did to get these prizes, and I will follow that the remaining open questions which we are looking for, and we are trying to find a solution for them. I will start with a paper who is written by a genius, Albert Einstein, and I will talk that what is about that paper and what they challenged about the quantum mechanics, and then I will continue to talk about the entanglement and the solution of finding the answer for this paper, which is called Bell inequality. Then we will go through that, what is the loopholes, Bell loopholes, and what people did to get the Nobel Prize, especially Clauser, Zeilinger, and Alain Aspect. And then I will continue the questions about the CMB radiations, which we can use it to, there's a mysterious questions about quantum Bell test, and we would like to answer it. And I hope that at the end of the seminar, I get some suggestions, some comments from your specialist, because this is your specialist field, and I'm not so familiar in this field. And your suggestions, your comments are really appreciated. And please feel free whenever you have a comments or whenever you have a questions. Okay, let's make the long story short and start from the quantum mechanics. As we know that the quantum mechanics started around 19th century with some brilliant minds like Heisenberg, Dirac, Born, Schrödinger, and many other peoples. Notably, Schrödinger developed an equation which is famous, which is well known as Schrödinger's equation. This equation shows that the evolution of an object, state of an object during the time. And solving this equation gives us the wave function which these wave functions, square root of these wave functions, gives us the probability of density finding an object in a specific state or in a specific position. Probability, a mysterious word in quantum mechanics. When we are talking about probability, when I'm saying that, okay, this is an object, I can see it, so I'm sure that it is here. But when we are talking in the quantum field or quantum mechanics, we couldn't say that, okay, this object is exactly here. We should talk about the probability. It may be here or somewhere else. And this mysterious word was not accepted by Einstein. There is a famous debate between Bohr and Einstein. They usually talk about these topics and Einstein says that, okay, I'm convinced that God does not play a dice. And he wanted to show his doubts about the quantum mechanics. We couldn't talk about the probability, or reality. Einstein believed that when the object is here, it is real, is here, and we couldn't talk about the probability. It may be here or may not be. And Bohr answered that, okay, stop telling God what to do. This debate caused Einstein wrote a paper which is famous as EPR paper, or the first letters of the names of the three writers, Einstein, Podolsky, and Rosen. And in that paper, they tried to challenge quantum mechanics. They tried to say that, okay, quantum mechanics is not complete and it should be completed, or there are some spooky actions or some hidden variables should be added to this theory. To make emphasize that how much this paper is important, this paper is published in 15 May, around 10 days before. It was in the New York Times journal. It was written that Einstein attacks the quantum theory. And it is interesting that it was written that scientists and two colleagues, the scientists sure that Einstein, who got the Nobel Prize in that time, says that, okay, a scientist and two other colleagues together challenged the quantum mechanics and says that quantum mechanics cannot be complete and it should be improved. What is the paper about? The paper is just a mental experiment, a thought experiment they wrote in this paper. They says that, okay, imagine that we have two particles, black and white, and they are correlated with each other in a way that if we measure the properties of one particle simultaneously, the corresponding properties of the other particle also determined. It means that this concept, it is a constructed or violated the Einstein's special theory about the relativity. It means that the information couldn't transfer faster than the speed of light. So if we have two objects separate from each other, and we measure properties of this object, and simultaneously we know that determine the other object's properties. It means that some information from this object sent to the other object, and we are violating the Einstein's special theory of relativity. So by this thought experiment, they claim that the completeness of quantum mechanics, they suggested that, okay, this spooky action, this spooky action is because of maybe we are missing some hidden variables, some variables we don't know about it, but these variables can send data from this side to this side. So, but this famous paper, EPR, they questions the completeness of the quantum mechanics. After this paper, Schrödinger prompted that, okay, we can say these two particles are entangled, and this entanglement are the characteristics trait of the quantum mechanics. What does it mean? It means that we have two particles, they are entangled. It means that they are correlated with each other, and the determination or preparing one of the state definition and the properties of one of the states has simultaneously influenced the other parts. These two particles are entangled and they are correlated with each other. Whenever I do some measurements on this particle, the other particle also change or rotate in the same way. And it is very mysterious and interesting, and many people doesn't believe this one. So this debate, so we have few scientists who claim that, okay, quantum mechanics is not complete. We need to improve it, or we need another theory to describe these phenomena. And some of them, like Schrödinger, both believe that no, quantum mechanics is true and believe that, okay, this field works. Until 1964, this debate exists. No one couldn't tell that, okay, I'm right or you're right. So in 1964, John Bell developed an equation which is famous as Bell inequality, gives us a means to examine, to test this debate and find that, okay, did the quantum mechanics describe well or not? He said that, okay, let's to think about Einstein's thoughtful experiment. We have two particles which they are entangled. It means that their properties are correlated with each other. Measuring of one particle's properties simultaneously influence the other particles. They are entangled. So consider the Einstein's EPR paper, and we have two particles. These two particles are measured by Alice A and B. So we have two observers, Alice and Bob. They are going to measure the properties or state of these two particles. What they are going to measure, can be anything. For example, direction. Suppose that we have two photons. These two photons has polarization, so the polarization have some direction, and we are going to measure these directions. We call it this property as A or B. So Alice choose an A and measure the properties or the direction of the polarization of that particle. Bob choose B and the direction or properties of that photons. Bell said that, okay, we suppose we have a missing variable, or that can transfer the data from A to B. We call it, this is a hidden variable. And we put it with the parameters lambda. So we have a hidden variable which determines that which direction we are going to measure and direct it and influence the particle to be in that direction. We don't know what is this variable. We call it hidden variable, but there is such a variable. So in Alice's side, Alice measures the properties of this photon or that object. In Bob's side, also they measured. And then we defined a correlation coefficient E between them. So we have a correlation. For example, we have a particle in Alice's side. Alice measured the particle is in this direction. Bob also measured in this direction, so they are correlated. The number with this correlation is 1. So we measure that, okay, we are measuring in this direction, but it is an other direction, so their correlation is 0 or -1. So we have two numbers, 1 and -1, and for correlation. And then he developed an equation, something like this. We measured the coefficients for different angles, and then we put it in the equation. And if the number of this equation is less or equal to 2, we believe that, okay, there is some hidden variables that says information to transfer information from one side to other side, and it is working. If we violate this number, if our measurement is larger than 2, it means that quantum mechanics works and there isn't any hidden variable to explain this phenomena. So we should believe on quantum mechanics. In 1964, he developed this formula, and now the scientists had something can be tested in the experiment. Can we go to the lab and to see that, okay, we have some measurements and put the measurements numbers in this equation and to see that, okay, what is the number? Around 1970, John Clauser, the first person who got the Nobel Prize in 2022, improved this equation a little bit, which is famous as CHS, the four person who did this equation, Clauser, Horn, and Shimony and Holt. They improved the equation a little bit and going to the lab to see that, okay, what is the measurement and what is the result? They used a laser, a lamp laser, and they pumped it with 2,275 wavelengths, and they generated two photons. One photon in 5,513, and the other is in 4,027. And these photons are entangled, and they go to the lab and measure the polarization of these particles. Interestingly, this is the setup. They did it. They generate two photons. One photon goes to the Alice side, the other goes to the Bob's side. And interestingly, they found that, I should mention that they changed the formula a little bit, and instead of the number of two, they make it is 0 or is smaller than 0 or larger than 0. If they go larger than the 0, they will violate the Bell's inequality, and in the experiment, they found this number. John's speech says that, okay, at the first time when we get, you can see that it is so near to the 0 point. So they thought that maybe they make a mistake or something like that. They did a few times the experiment, and they found that it is 6 times above the standard deviation, the number. So they believed, okay, yeah, maybe they violated the Bell inequality. So they answered these questions that, okay, maybe Einstein was wrong. Maybe quantum mechanics is complete and it can explain the things. Here, this is the result of the experiment. The points are the experimental results. The line is the prediction of the quantum mechanics. We can see that a good agreement between theory and the experiment. So by the tools that John Bell developed, and after that Clauser used it, they proved, okay, now we are violating Bell inequality, and now we can say that, okay, maybe Einstein was wrong and quantum mechanics is complete and we don't need any hidden variable. These mysterious questions has been answered. But there are some doubts on this experiment, which they call it loophole. What is the loophole? The loophole is that any conditions on any limitations that may affect our experimental results, it might affect our result, but we couldn't remove them. So for example, when some of you are experimentalists and you are doing some experiment and you should assume something that, okay, we assume that this is true and then continue the experiment. And the scientists claim that maybe these assumptions make you violate the inequality. One of them assumption is that the main assumption is that locality loophole. What does it mean, locality loophole? Suppose that I have two particles, I measured one of them, and I said that, okay, measuring one particle simultaneously affect the results on the other side. So suppose that when I measured this, there are some times that some hidden variables transfer data from here to here. So this particles knows that what I measured, so he changed in a way that I violated the Bell inequality. It is called locality loophole. Means that suppose Alice here do some measurement, and the data from her measurements send information to this one and affected this one without I know this is happening. So it is necessary to close this loophole. How? I'm going to do some measurements in Alice sites, and I told that we are going to measure the direction. I'm going to measure this direction or that direction. So which one? It is random. So in X position, I choose the direction, for example, X direction or Y direction, and then I do the measurement. When I choose the direction, it should be some data from my selection to send to the Bob site. But I know that this data couldn't be faster than the speed of light. Yeah. So I choose my setup for this direction. The data should be sent to Bob's site. If I do the measurement in this grayscale, the data couldn't be transferred to the Bob site, because if I choose here, the data wants to transfer to the Bob site needs to be, the speed of it should be more than the speed of light. So it couldn't be happen. If I choose the data here, the data can transfer to the Bob because this is less than the speed. This is the speed of light. So if my data chosen here, the data has not been transferred to the Bob site. Bob doesn't know anything about my selection. If I choose the data here, Bob can get some information by some hidden variable which I don't know. So for closing this locality loophole, it is necessary to choose settings in this area as fast as possible to make them not, it couldn't send the data to this part. This is done. So this is another diagram of this space diagram. We have Alice, we have Bob, or Alice Bob. Alice wants to do some measurements in his regime, in his lab. Bob also wants to do some measurements in his lab. Now, Alice choose a direction, this direction or that direction. And if it is fast enough that they couldn't send the information from this side to this side, so we can close the locality loopholes. Alice's side couldn't send information to Bob's side or vice versa. Alain Aspect, for the first time, closed this locality loophole, and because of this, he got the Nobel Prize, the second person who got the Nobel Prize. For closing this locality loophole, it is necessary to separate Alice and Bob from each other and do the measurement fast. This is the results of this is the experimental setup of them, and this is the result. As you remember, we have the inequality on 2 and -2, and here we can see that we are violating, the results are more than 2, and we are violating the Bell inequality. And this is the first time they closed the locality loophole. Here, I should add this beautiful island to the experiment. We have a lot of experiment here, which has very impact on this development and these achievements. The first one is this beautiful figure and this experiment. This is the longest locality loophole closing experiment which is done until 2017. This experiment has been done between this island and Tenerife. The distance between them is 144 kilometers. I know that you know better than me these islands. And we use 2 telescopes, one of them in La Palma, the other is in Tenerife. We used Jacob's Captain telescopes and optical ground stations telescopes. We put our source here. The entangled source was in La Palma. Then the photons from La Palmas by free space has been sent to the Tenerife. We collected the data in Tenerife, the other data, so suppose that Alice is in Palermo, Bob is in Tenerife. We send entangled photons here. Now, we choose by randomness some directions, this one or that one, and we measured the properties of that photon and look at the correlations between the Tenerife side. And they violated the locality loopholes, and it is published in Nature. So Until now, we found that we violated Bell inequality, and there is one locality loophole. We can close it. For example, the best one is the one that we did in the Canary Island. The other crucial and important loophole is that freedom of choice loophole. What does it mean, freedom of choice? So back to the mental experiment which Einstein suggested. We have two photons. We have two objects. Measuring of one of the objects simultaneously affect the second one. For measuring on this object, we need to choose which direction we are going to measure. For example, this direction or that direction. This is completely random. We randomly choose this. We are going to measure this direction or that direction. And now the scientists claim that you are going to choose a direction, but this is not a random or free. Some variables affected your selection. Suppose that you have a source. Your source generates two entangled photons. When these two entangled photons are generated, here, there are some hidden variables has been sent to the my choose, for example, A or B, and they said that, okay, you should be in this direction or that direction. So my selection is not free. My selection has been determined by someone else here. So to close this locality, to freedom of choice loophole, it is necessary that we look at the source and, for example, suppose that we have a missing variables here. They want to send the data to affect or determine my setting choice. So before that particles receive to my selecting setup, I choose the setup. So before the information comes from the source, I select the setup and then I do measurements. So if I can do this, I can close this freedom of choice loophole too. This is done for the first time again in this beautiful island in our groups. In 2010, our groups simultaneously both closed the both loopholes, freedom of choice and locality loophole. How? We used Palma and Tenerife Island. We separate the entangled source from each other. It means that, for example, I have Alice here, I have Bob here. So if I do some measurements on Alice's sides, if Alice they want to send the information to Bob, they are around 100 kilometers far from each other. So the information couldn't transfer from Alice's side to Bob's side. So we close the locality loophole. Then we want to close the freedom of choice loophole. So my random generator, the setups that choose which direction I'm going to measure, we separate from 1 kilometer from the source. We separate them. Now we can close the freedom of choice. So this is done for the first time in the world in this island, and we published it in PNAS journals. So we closed the locality loophole and freedom of choice loophole simultaneously. The third loophole is the fair sampling loophole. What does it mean? It means that we have a lot of object photons and we are measuring in the lab. We couldn't detect all of them. We need to make a subset of these photons. We have a lot of ensemble, we have a large set, and we couldn't detect all of them. We need to make a subset of this set, the whole set. And we should make sure that this subset is not biased in a way that what we are looking for or what we are expecting to see. This subset should be in a way that determined be a small area of the large subset, our main ensemble, and it should show the behavior of our whole systems. So it means that as much as possible, I should gross my detection data to close this fair sampling loopholes. And it can be done by fast detecting and high efficiency detectors. In 2015, there are 3 groups independently close these whole loopholes. So we have 3 loopholes. One of them is locality loophole, one of them is fair sampling, and one of them is freedom of choice. In 2015, 3 groups independently closed this loophole, and they proved that, okay, without any doubt, we can violate the Bell inequality. One of them is done by Delphi University in this October of 2015. The other was done in our groups in 2015 in December. They published it. And the other was done in NIST Boulder University. Just a short look at for this experiment. In this beautiful diagram, we can see the violation. The photons generated here, and if there is some data or some hidden variables wants to send information to my setting choice, it should go in this blue line. Before this data received to Alice's side, I choose my setting. So I'm closing the freedom of choice loophole. Then I'm doing the measurement. This is the measurement time. Before my measurement send some information to the Bob side from here, I'm closing it also. So I'm closing the locality loophole, and by detectors, I'm closing the whole loophole simultaneously. Okay. Until now, we found that 2 persons got the Nobel Prize, one of them for violating Bell inequality, the other for closing the locality loopholes. One of the advantages of the quantum information is quantum teleportation. What does it mean? It means that we are going to transfer a state of particle from this side to this side. We should be careful that we don't transfer the whole particle. We're just transferring the state of the particle. How it can be done? Suppose we have 3 particles. One of them, the initial state. This is the state that I want to teleport. This is the state I want to teleport from here to here. And I have an entangled source. This is entangled source, described with this formula. I can rearrange this formula like this. So I can rearrange. So I have a particle 1 with the initial state. I have 2 particles 2 and 3. I can rearrange it in a way that I can write particle 3 in this way, and the other 1 and 2 in combination of the Bell states. If we look carefully, the initial state, this one, is this. So if I combine particle 1 and particle 2 in a way that it is a psi minus, I can make sure that, okay, the third particle, this one, the state of the third particle is the same as the state of the initial particle. So what I'm going to do is, I have a 1 particle from this part. I have entangled particle. One of them go to combine with the first one. The other goes to the other side. And I want to transfer the state of the first one to the third one. How? I should make sure that, okay, when I combine on the beam splitter the first and second particle, the state should be sinus 1. It is done by the third person, Anton Zeilinger, who got the Nobel Prize in 2022. For the first time, they did this teleportation, this groundbreaking experiment they did successfully, and they transferred the initial state from here to the other part. And again, it is interesting that this beautiful island has a great impact on this experiment too. the longest teleportation has been done in this island between the Palma and Tenerife. They generated entangled source here. They generate the initial source was here, and then they teleported the state from the Palma to the Tenerife. This is the longest teleportation has been done until yet. And this job was the beginning of doing the experiment with satellite. And they published in Nature 2012. Okay. Until now, we go a short history of the 3 persons who got the Nobel Prize. The first one for experiment with entanglement. The second one who established the violations of Bell inequality. And the third person, Anton Zeilinger, for pioneering quantum information science and his works in this field. He did, for example, teleportation, closing the loopholes, and so on. Is it closed? Is it the questions which started by Einstein has been answered? We should say that no. And it is because of the fair sampling. It is what we are looking now. We said that we have 2 sides, Alice and Bob's side. We are going to choose a setting for the direction, which direction we are going to measure. And we claim that it is not free. It may be some hidden variables dictated to our choosing. And we closed it by supposing that this unknown particle should be generated when our source has been generated 2 entangled photons. It means that our source generated 2 entangled photons, and simultaneously some hidden variable sent in when they generated the photons, also simultaneously another hidden variable send information from the source to Alice or Bob. Yeah, this is our assumption. We assume that the experiment started when the source generated entangled photons. But there's a question. What about if these hidden variables come before generation of the source generated? It means that my source generates photons here, but before that, some unknown variables and some unknown things that we don't know about it dictated our settings. Choose this setting or that setting. Yeah, is it clear? We are looking for the, okay, we said that the experiment, the time 0 of the experiment is when the photons are generated. Now the question is that, no, the 0 point is when the universe started. It means that something before the photons has been generated tells that, okay, the photons should be in this direction and our setting choice should be in that direction. Some unknown variables affected our experiment. So what should we do to close this? We can think about a random generator, which is very long ago has been generated. And we looked, and the best choice is that something from the astronomical and cosmic, from the sky. We know that, for example, the quasar is an object as many years ago. This is the oldest object we can observe in the sky. So if we look at the quasar, for example, 7 million years ago, and we use this quasar as a random generator, it means that the photons which coming from the quasar 7 million years ago has been generated, and we are using that photon as a random generator. For doing this experiment, we use these beautiful telescopes for TNG and WHT, William Herschel telescope and telescope of Galilei. It seems that these 2 telescopes in Palma has been constructed for our job. It was very interesting. Both of them has almost 4 meters diameters of the observation mirrors. And also the distance between them was about 1 kilometer. The distance which we need to close the loopholes and the diameters we have to look at the quasar and to observe the quasar. So it's very interesting. We use these telescopes to do our jobs. So the question is that how we can use quasar as a random generator, how we are going to use the quasar as a random number generator. This is a photo of quasar. This is the light comes from the quasar. So we know that the quasar's light has a wavelength, a spectrum of wavelengths, which can be red, blue, and many wavelengths inside it. We split the wavelengths to blue and red by the beam splitter. So we are getting the light from the quasars. We divided the light and name it blue and red. So when we got the blue photon, we said that, okay, our random generators is, for example, choose this direction. If we got the red light, we just said that, okay, our random generator is, for example, in that direction. So we have a setup using a quasar 7 million years ago as a random generator. And we know that, okay, our experiment has not been affected 7 million years ago by anything else, because we are using a random generator with 7 million years ago. This is the whole setup. We look at the quasars. We use these quasars, one of them 7 gigayears ago and one of them 12. And to my knowledge, this is the brightest quasar has been observed until now. We look at these quasars and we use the light of these quasars as a random generator. The light comes from our random generator. We split them. When the blue, we choose one of the settings. When it is red, we choose another setting. Our entangled source generate 2 photons and send to the telescopes. If you look at this, this is the setup, yeah. We put our source here in the middle, around 500 meters from the one of the telescope, 500 meters from the other telescope. We look at the quasars and we do the measurements and look at the result. Our result, first, we assume that the wavelengths of the quasar photon do not selectively alter or preview between emission and detection. It means that when we are looking at quasar, nothing has been affected the light when it is propagating from the quasar to us. We assume this. We need to assume that, okay, the quasar's light has not been affected by anything else. And we got the violation of Bell inequalities 9 standard deviation. So Alice, Bob measures, the source is here, and we looked a long times ago to see, okay, our settings has not been affected 7 million years ago. Now, this is our problems. Now, is it possible to go further back? Is it possible to go to look at when the universe starts? The oldest and the farthest light has been observed until yet is a CMB radiation, cosmic microwave background radiation. These radiations started about 300,000 years ago after the Big Bang, and we can detect now. The question is that, is it possible to use this light as a random generator? In our mind is that, yes, if we can detect the time of arriving of these photons, and we found that, okay, we have some bands. I know that you are a specialist in this field and I am not so familiar. We know that you have some bands in these regimes to detect. For example, you call the 3-band and 4-band. You have some detectors in these bands, and we want to know that, okay, if we use these band, for example, as a random generator, for example, 3-band or 4-band, when we get photons in 3-band, we choose one of the settings. When we get 4-band, we choose another setting and use these radiations as a random generator. Then we do the experiment. Now, we are looking for that to close the freedom of choice loophole. We are looking to close the freedom of loopholes by looking at CMB radiation, the oldest light we have now, or we can detect now. So the time is finishing. So the conclusion, I talked about the Nobel Prize of 2022, and I talked about our problems, which is the freedom of choice problem, and we are looking to close it by looking at the CMB radiations as a random generator. And I will appreciate if you have any comments, any suggestions, or to let me know. Thank you.
Thanks a lot for the talk. So we have now time for questions or comments. So.
Well, I have a few questions. First, if I understood correctly, in the transference of information of a state, you can do it only 1/4 of the time, because you have to measure, and when you measure in phi minus, you happen to measure in phi minus, then you have this correct, but not in the other cases.
Yeah.
Is that correct? Or?
Yeah, we look at a subset of a large ensemble.
Mm-hmm.
We have, for example, we detected photons, single photons, and we look at the correlation of these single photons. Yeah. Mm-hmm. We look at both photons simultaneously, and we look at the correlations of the photons. But since we have ensemble, for example, we have 1,000 photons in this side, 1,000 photons in that side, and we look at them. Our detector shows 1,000 photons, but each of the photons, we look at the correlation of each of them.
Mm-hmm. Okay. Mm-hmm. There was something that confused me when you, the first, sorry, the first expression that you gave for S, the quantity that entered the Bell inequalities, it was not symmetric in A and B. Was that a typo or?
A and B, for example, it is the properties which we are going to measure. For example, the polarization, H polarization or B polarization. A and B is this one. And
yes, that's clear. But the expression that you show, can you show it was the first expression that you gave for us when you were talking about the generalities about Bell inequality.
Here?
Yes, that one.
Okay.
It's not symmetric in A and B. The quantity, the Bell CHSH, the quantity that the expression, the definition, the quantity S is not symmetric.
What do you mean by symmetric?
In A and B,
So in A, for example, we look at one direction. In B, look at, for example, 0, 0. A, B prime is about, for example, randomly choose.
Yes, that's clear. But if you change A and B, there is a sign there change. That does not remain the same if you exchange A and B.
Why?
Why? Because
A and B, so this should
A
be
and B and A prime and B prime.
And B and A prime and A prime B.
Yes, but the one A
so
B
here,
prime.
So here A prime B changed B A prime. This is this. This one.
Know.
So if this is prime, so prime comes here, so the minus again the same. So we have A and B, A prime and B prime. If we change, this is the same, yeah? But here, if I change A prime by B, so prime is here and again.
Mm-hmm.
Yeah.
But
so
the second, I saw a second expression and was symmetric.
Here, for example, A and B, if I change A and B, it is the same as A prime.
Yes, A and B, but you
Here.
can A and B and A prime, B prime.
So A with B prime and B prime is firm. So this is
Okay, well, it's
Yeah,
correct. The expression is
yeah.
correct. Okay, just confused me. And well, another question is that I've been surprised that you try to prove this freedom of choice, because that is it's very strange. I mean, you're almost trying to prove the freedom of the will, the freedom of will, no? Supposing that there is a variable, a hidden variable that can influence the choice that to make. Well, it's something. In the end, as you know, the metaphysical determinism cannot be falsified. I can tell you that there can be some hidden variables just at the Big Bang determining everything. If you want to believe that everything,
exactly.
that everything is written, you can believe it. And physics is not going to falsify that.
Yeah.
So, well, it is interesting, but I was surprised that you went all that way to try to test that.
To be honest, what Anton thinks that he thinks that okay, we should go to the starting Big Bang point, but now from the Big Bang we don't have any information or any data. The last things that we know and we can detect is now is called CMB radiation. So we are trying to prove this. If we hope that we can do it, and after that we should think, okay, is it possible to go further again or not?
Thanks for a really interesting talk. I'm no way an expert on this, but I read a Nature paper recently on something called the Big Bell experiment, which used, I think, 100,000 online gamers to make random choices.
Yeah. It is
to
another
close this loophole. So, what's your opinion of that?
Yeah, for random choosing, there was an interesting idea, and it was that there are a lot of ways to choose a random generator. We can use a machine. We can use, for example, light. We can use quasar. And a fantastic idea was that we choose people to choose that, okay, which direction to do these measurements. And it was published in Nature. They designed a software, an application, and they separated between people. And they asked, okay, choose between the A and B for this one. So they choose people as a random generator. Many people contributed to this test, and it is published in Nature. And the interesting thing is that it was not completely random, because for example, you are choosing between 0 and 1. You choose zeros. If you use machine randomly choose between 0 and 1. But people usually, okay, 0, 0, it is in your mind that, okay, I typed 2 times 0. Let's go push 1. People never times 10 times 0. Yeah, this is so they use the people as a random generator, but yeah, and they prove that, okay, people also, if we use people as a random generator, we can violate the Bell inequality. But yeah, this is true that they did it. But I should add that it doesn't answer our question. Our question is that we should look at the when, maybe also these people has been affected by some unknown variables, all of them. So we should look at the past, something that from the past we received. Yeah.
So I want to go back to the comment about the ultimate freedom of choice. Would you agree that there is the possibility that there's some hidden variables that have determined everything, that there is no free will, right? And that whatever experiment you do, you don't get around the possibility, right? That there is, well, but that's what you're doing. You're doing philosophy now.
Yeah.
And it seems like if you really want to push on the freedom of choice, there's at the beginning of everything is something that you can't test unless you have some ideas to test that, and that would be very interesting.
Yeah.
You agree with this?
Yeah. It's a philosophy question.
So there's time for one more question. We'll see more questions.
Going back to the philosophy questions, do you have like a favorite interpretation of quantum mechanics, whether the many worlds or whether you have locality or determinism, or the Schrödinger equation describes everything, or just in case if you have any opinion on that?
Yeah, the quantum mechanics, yeah, and we talked about it. The debate was that whether about the realism or about the reality and about the locality and non-locality. The question started from here, and the things that Einstein believed that about that we have a reality and the classical physics based on the reality, but quantum mechanics says that okay, maybe we should think more about it because we are violating by entanglement that okay, where entanglement exists, but it is a fundamental basis of the quantum mechanics, and we have no evidence. Okay, what makes them to be entangled to each other?
All right. So let's thank the speaker once again. And I would like to remind you that now we have the scientific coffee in the cafeteria, and for the students to come here to check the attendance.
Thank you.